So I think that one of the most pleasing things about learning mathematics is that one becomes aware of the rich kind of shapes and forms which lie behind seemingly mundane things that happen in the world. So, for example, consider somebody throwing a projectile. So they throw, let's say, a ball and it goes in this kind of curve. It flies through the air and then it falls down to the ground. Now, we see this, it's a very everyday kind of occurrence, and then maybe later we go to school, we learn about gravity, we learn about acceleration, we learn about parabolas, and we can start to apply mathematics to understand what's going on. But as one goes sort of further into mathematics, one can have a richer view of something like this. And I find this very, very pleasant because we can actually start to connect these very much sort of everyday happenings like the trajectories of projectiles, and we can connect those with really rich kind of high dimensional geometry. And so what I thought I'd do this time is to speak about what I'll call the 5-dimensional geometry behind a projectile's motion. Okay, so we're really going to look at something that on one hand is very, very simple, and it's something which hopefully everyone will be able to follow. The mathematics is extremely simple, but on the other hand, we're going to then visualize our results as something that's happening in 5-dimensional space. But it's a very pleasant kind of viewpoint, because even though what we're looking at is happening in 5-dimensional space, we're going to be able to sort of decompose the problem into things which are happening in 3-dimensional space. And we're therefore going to be able to make sense of what's going on. And the real point that I'm trying to illustrate here is this kind of usage of what physicists call phase space. Okay, so the idea is basically that if you have some kind of physical system and it has, let's say, a few inputs, a few sort of degrees of freedom which are governing what's going on, a few numbers that you put in at the beginning, and then it does something, then you can think of each of those kind of inputs as a different dimension, a different kind of number that you can vary over. And in this way, you can visualize all sorts of physical systems as things which are happening in high dimensional space. And what we're going to do is look at this very, very simple situation of the trajectory of something that's being thrown. And we're going to think about what the different inputs are and what the different outputs are. And we're going to really visualize what's going on. So there's sort of two parts to this. Firstly, we're going to describe this projectile motion, and that should hopefully be quite straightforward. And then secondly, we're going to think about how we can visualize what's going on as something happening in 5-dimensional space. And we're going to also think about how we can build up that picture and really understand it in terms of things that are happening in 3 dimensions. Okay, so what I'm really trying to do in this video is, one, to describe the trajectory of our thing that we're throwing, and 2, to relate that to 5-dimensional space, and 3, I want to sort of break down that picture in 5-dimensional space into a way that we can really get our minds around it by thinking about stuff in 3 dimensions. And what I'm really trying to get across in this video is the sort of richness of everyday happenings when we think about them in terms of high dimensional geometry, which you'll see is actually surprisingly easy to do. So we begin with this projectile. Okay, we're going to throw this, let's say it's a ball, doesn't really matter what it is, but we're going to throw it, and so it's going to have some kind of initial velocity. And then the only thing that's going to happen is that this thing's going to fall under gravity, so it's going to accelerate downwards. And so what we can do for a start is we can think about the velocity in two different components. Okay, so if you think about the velocity, so you can think about the velocity as an arrow. Okay, it's going to be giving us the rate of movement of this ball. Maybe we're measuring it in meters per second or miles per hour or whatever. We're not going to worry too much about the units, but we're measuring basically how much distance this ball is going to be covering in a unit time. But we're also going to think that there's a direction that the ball is moving in. So we could really represent the initial velocity of our ball by a vector, by an arrow pointing out of the origin. And the bigger that arrow is, the more velocity this ball has. But given the nature of our problem, it's very useful if we actually break up this vector into two other vectors, two other arrows, a horizontal one and a vertical one. And the thing that we're doing here is we're thinking of this situation as happening in two-dimensional space, and we're thinking that there's going to be a horizontal component of the velocity, so we could call that v subscript x, and there's also going to be a vertical component to the velocity, so we could call that v subscript y. And so, for example, if you were a scientist studying this kind of situation, maybe you could put some kind of sensors along this kind of x-axis, and these would detect where this ball is with respect to this line over time. And then, maybe at time 0, you detect that the ball's here, and then at time 1, the ball's here, and then at time 2, the ball's here, and so on. And so in that way, you would just be looking at this system along the x-axis. So you would only be concentrating on the kind of horizontal component of the ball's motion. And so what you can really do is you can sort of decompose this problem into a sort of horizontal component and a vertical component. So the horizontal component, if you're looking at that, that's telling you how far the ball is kind of moving to the right over time. And in fact, the way that this ball is going to move horizontally is really very simple, okay? Because we're going to assume that there's no air resistance, and we're just going to assume that the ball is just launched at this initial kind of horizontal velocity, Vx, and then it's simply let go, okay? So this ball is simply going to keep moving to the right at a constant rate. And yes, the motion of the ball in the other direction, in the kind of vertical direction, is going to be more complicated because we've got gravity making the ball fall down and so on. But the point is that we don't have to worry about that when we're thinking about what's going on horizontally. We can really decompose this problem into sort of two different problems. One of them is understanding the horizontal motion of the ball, and the other one is understanding the vertical motion of the ball. And concerning the horizontal motion, the problem is really very, very simple, okay? So what we're interested in is going to be describing where this ball is at a particular time, okay? So we're going to be thinking of time, t, as something that changes. So t is like a number measuring how much time has elapsed. When t is 0, the ball is here. So we're assuming that this ball is sort of thrown at time 0. And then at any given time, there's going to be an x coordinate to where the ball is, and there's going to be a y coordinate to where the ball is. And as we change this time t, the ball's going to move along its trajectory, which you may have guessed is going to be a parabola, but we'll get to that later. But the point is that if we just start by thinking about what's going on horizontally, then the situation really looks very simple, because we know that the amount that the ball's gone from the origin is just going to be equal to the amount of time which has elapsed multiplied by the velocity that this ball has. Okay, so it's really very simple. It's just that the displacement is equal to the time multiplied by the velocity. Okay, now we are making some assumptions here. As I've said, we're assuming that there's no air resistance. We're also going to assume that this ball never hits anything. Okay, so we could imagine, for example, that we've launched our ball from an infinitely high ladder. Okay, so the ball can just continue to fall and it never stops. It's not like it hits the ground at some point. The ball is allowed to kind of drop below the height it was initially launched from. So we'll just assume that this ball just continues forever. So, okay, we've got this kind of equation now, which is giving us this sort of horizontal motion of our projectile. And it's very, very simple. Of course, this is something that we've all learned that since we were very young, is just that displacement is equal to time multiplied by velocity. But I think it's still quite interesting to sort of step back and think about what this really means. So at the moment, I've written x of t equals t times vx, but really, it will probably be more sensible to say that this displacement x really depends on the time and the velocity. Okay, and it's equal to the time multiplied by the velocity. So how can we think about this? Well, really, we can think about this in terms of functions. Okay, so we can say that we have these different inputs, time and velocity, and those are both going to be numbers. Okay, so we can choose those two numbers. Let's say they're real numbers. So I'll use this scripty R to denote the set of real numbers. And so what we have is this situation where we're picking a pair of real numbers and so I'm going to write R times R. Basically that is the set of all pairs of real numbers. And we have this function that we're calling x, and it takes in a pair of real numbers and it spits out a real number. Okay, so really this kind of situation is that the first real number is going to be, let's say, the time. The second real number is going to be the velocity. So we'll say Vx, and we could pick those to be whatever we wanted, any real numbers we like, any members of these sets. And then the output is going to be another real number, which is the displacement, and that's going to be t times v of x. Okay, so here this times is multiplying numbers, and this is something a bit more interesting. This is what you call the Cartesian product of sets. It's where you take two sets and then you form the set of all pairs with the first entry from the first set and the second entry from the second set. Anyway, and this would often be written a bit more concisely as r to the power of 2, or the set of all pairs of real numbers. So how can we visualize this situation then? This very, very simple situation where basically we're just saying that the displacement is equal to the time multiplied by the velocity. Well, what we have is a situation where we have these two kind of inputs, t and vx, and then this output, which is t multiplied by vx. So you can think of this as a sort of situation. Let's say you were doing experiments in physics and you were varying these two different numbers, you know, the initial velocity that you're throwing something out at and the time that you're going to look at it at, and then you're going to record the displacement. So you have all of these experiments where you have two inputs and one output, and then you might want to plot or visualize what's going on. So how would you do it? So we can really do this with a sort of three-dimensional plot, okay? What you might call a surface plot. So basically the situation is something like this, okay? We have one axis, which is giving time. So this is going to be one input. So maybe the time might be 0 or 1 or 2 and so on. And then we have another axis, which is going to be giving our velocity, Vx. And we can choose that to be what we want. And so then when we've picked, say, a time, let's say 2, and a velocity, let's say 3, so we can think of those two things together as corresponding to a sort of point on this plane. And for each such point, we can plot our kind of output, which is going to be the displacement that we get when we're moving at that velocity for that amount of time. So the way that we can visualize this is that we then have a third axis that we might call x, and there's going to be a sort of surface, which I'll visualize properly momentarily. And this is really telling us how x depends on t and v of x. In particular, if we pick any sort of point, say this one here, where we have t equals 2 and vx equals 3, and then we draw a sort of vertical line up to the surface, that's going to meet the surface at the point x of t comma vx, or in this case x of 2 comma 3, which is going to be 2 times 3, okay, in this case, and we won't worry about units at the moment. So the point is that we can really visualize what's going on in this situation. We can visualize this kind of function here as a sort of two-dimensional surface in three-dimensional space. And so let's have a closer look at the actual nature of that surface, because it's pretty interesting. Okay, so we have this equation of motion, and what we want to do is to visualize this as a surface in 3 dimensions. So we're going to think that we have 3 numbers. We have time, t, that's given by this red axis, and we have the horizontal velocity, vx, that's given by this green axis. And so we can think that we have a sort of plane, and the points in the plane, such as this point which I'm moving around, have coordinates which correspond to those numbers. So any point in this kind of grey plane is going to correspond to a specification of a time and a velocity. And what we want to represent is that the displacement is equal to the product of these two things. And so we're going to draw a surface that's height above a given point in this plane is equal to the product of the two coordinates of that point. So for example, if we pick this point here, where t is equal to 2 and vx is equal to 3, then we would like the surface height above this point A to be 2 times 3, which is 6. Okay, so what we've done now is visualize this kind of surface that we wanted to think about. So we're still moving our original point around inside this kind of plane, this kind of tvx plane, if you like. But now we have this surface shown in light blue. And the idea is that if we pick a point such as this blue one inside our tvx plane, then the height of a point above that in the surface is going to be equal to the product of the two coordinates. And so essentially this surface is describing for us what the displacement is going to be. given a particular value of the time and the velocity. So, okay, I'd like to visualize one other thing about this kind of situation, and that's basically about what happens if we just pick a particular velocity. So this is maybe a more natural way to think about this kind of situation. So if we just sort of pick a particular velocity, let's say a velocity of 1. So if we just slice this kind of surface across with this plane of the places where Vx is equal to 1, then essentially what we get is just this straight line. And what this is telling us is that if we just fix this velocity to be 1, then we're going to find that the displacement x goes up linearly with time. Or we could think about what happens when the velocity is 2, or even when the velocity is -1, in which case the projectile would be moving backwards. And we can see that whatever velocity we pick, the displacement is going to change linearly with time, because that's the nature of our equation. So let's, for example, fix the velocity at 1, and then we can sort of rotate around our situation so that we can just make a plot showing how the displacement is going to change with time. And that would be a sort of two-dimensional plot. But an important thing is that this surface is actually telling us about how movement works whatever velocity we pick. And it's also interesting that you can see that even though this surface is curved, it's actually, in a sense, it sort of consists of all of these straight lines. So if we just look at one of these straight lines, you can see that the straight line is completely contained within this surface. And this all makes perfect sense, of course, because if we pick any particular fixed value for Vx, then we have this equation that x is equal to t times Vx, and those values are going to consist of this straight line, and they all should be within this surface, which is telling us how displacement is a function of velocity and time. So, okay then, we've had a look at the kind of way that this projectile is moving horizontally. So now let's do the vertical kind of component of this situation. So what do we know about this? So now we're going to think about what's going on in the vertical component. So here, the projectile is actually falling over time. So what we're going to assume then is that this projectile's launched initially with some kind of vertical velocity. I mean, we'd probably be thinking that we'd be firing this projectile up to start with. So initially, this velocity is perhaps positive, but then over time, this projectile is going to be falling due to gravity. And so we're going to assume that it's sort of decelerating, or its velocity is kind of decreasing at a constant rate over time. So let's have a think about that then. What we can think about is, what would it look like if we plotted the kind of vertical component of the velocity of our projectile over time? So here we've got time t, and we've also got the vertical velocity, so I'll call that vel, so I don't confuse it with the Vx and Vy symbols that I've been using earlier. So initially at time 0, we're assuming that the velocity is going to be Vy, okay, this initial velocity. Now, we're really thinking of that as something we can choose. Indeed, we're going to investigate the consequences of varying it, but for the sake of a particular launch of this projectile, of course, there is a specific initial vertical velocity. When we throw the ball, it's imparted a particular vertical component to its velocity. Or if you just sort of flip a coin in the air, then there's a certain speed at which it begins traveling upwards, and then it keeps sort of falling down due to gravity and decelerating. And so basically, because we're not going to model air resistance, what this means is that this velocity is going to continue to decrease at a constant rate. Okay, what rate are we going to assume? The ordinary rate at which things fall due to gravity on Earth, which is often called g, and typically people say it's 9.81 meters per second per second. The kind of rate of acceleration due to gravity that an object has when falling to Earth, assuming a vacuum and so on. And so basically what this means is that we're assuming that this line that I've drawn here, which is showing a sort of constantly decreasing velocity, that this line has a gradient of g. Okay, so if we change t, let's say from t to t plus 1, then we should imagine that during this unit time, this line is going to decrease by g. Okay, so we can think about this. We can then get an equation for our velocity. So in particular, we're going to have that our velocity is going to be equal to the initial velocity, vy, take away the time multiplied by g. Okay, so when time is 0, our velocity is our initial velocity, vy. But then after a certain number of time units have elapsed, we'd take off that many units times g from our velocity. And as I said before, we're just going to assume that this projectile just keeps falling over time. So it's not like it hits anything. It's a kind of odd model of a universe where this projectile will just continue to fall faster and faster and faster, even exceeding the speed of light at some point. But anyway, it's a mathematical model. So what we have here is a nice situation where we can do a little bit of calculus. Now, I'm trying to keep this video sort of gentle, so I'm not going to make a big deal out of this. So basically we have this velocity, and it changes with time, so we can think of it as a function of time t, and we've sort of argued that the form of this velocity should be vy take away g times t. So now what we're going to do is we're going to suppose that we then have the sort of a height of our ball at a time t. And this is going to be some function of time. Okay, but what do we know about this? Well, we know that if we differentiate this this function here of time, we ought to get the velocity, right? Because the rate of change of displacement is the velocity. Okay, let's suppose we don't really know what the form of y of t should be, but we do know that it's going to be some function of time. So if we plot time and we plot y of t, then we know it's going to be some sort of mystery function. But we also know that if we differentiate this function of height with time, in other words, if we work out the sort of gradient of this function as a function of time, so that's the slope, how much it goes up as we increase the time, then we know that that ought to have this particular form. Okay, so in other words, what we do know is that if we differentiate y of t with respect to time, then we ought to get the velocity at time t. And so we really want y of t to be some sort of function that has the property that if we differentiate it, we get this function vel of t here. And so then if we know a bit of calculus, we could have a good guess what this function y of t ought to be like. And it's probably going to be some constant plus vy times t, take away gt squared over 2, And it turns out that this kind of expression for y of t, the height at time t, does indeed have the right form. If we differentiate it, we do get this function vel of t back again. And in fact, we can do a bit more reasoning. We can say, well, let's suppose that at time 0, the height is 0. So that must mean that this constant alpha equals 0. And so we can rub it out. And this is then our sort of final expression for the height of our projectile at a time t. Cool. Now, there's a more sort of physical way that we can think about what's going on here. If we suppose that a certain amount of time elapses, say a small amount of time, then if we multiply that amount of time by the sort of velocity that our particle has at that time, which is going to be somewhere like this, then we're going to have a certain sort of area, and that's going to be a little amount of time multiplied by this sort of average velocity at that time, and that's going to give us a certain amount of displacement, which is going to be like how far this particle moves in that small amount of time. So if we suppose that our particle starts at height 0, and this is a sort of plot of its velocity, then initially its height's going to be sort of increasing as we keep adding these little bits of area. So the next sort of moment of time, we're going to have an average velocity like this. Well, the velocity is going to be approximately this, and then approximately this, and so on. And so we're adding up this area under the curve. And then eventually, we'll get to a point where the velocity is actually negative, and then we're going to be falling. Okay, so we're actually going to be decreasing our displacement then, coming back down to Earth again. And so adding up this sort of area under the curve, or basically integrating this function, is going to be giving us the displacement. And you can actually sort of reason out why this y of t should have this form just by thinking about areas of triangles in this case. You don't even have to use any sort of calculus to get at this result. So now we've really solved the kind of second part of our problem. We've understood the kind of vertical component of the motion of our particle. Okay, so I still find it quite remarkable that we can really think about this kind of situation by thinking about the horizontal and the vertical components in isolation to each other. But we can indeed do this. So now we've understood an equation for x of t, which is this, and now we've also got an equation for y of t, which is going to be t times initial y velocity, take away g times t squared divided by 2. And so, you know, some people would probably say at this point, well, we're done. And in a sense, we are. We have these equations, we can really describe the motion. But now I want to get into the kind of area of trying to visualize what's going on. So we've already visualized the kind of horizontal motion as a surface, and we can do something similar with the kind of vertical motion. We can also think of that kind of situation as a surface. Now we're going to have these two kind of inputs, which are going to be the time and the initial vertical component of the velocity. And then we're going to be able to map the height of our projectile as a function of those two things. So we've got this equation here for our height of our projectile as a function of time, but we can really think of this as also depending on our initial velocity Vy. Okay, we'll take acceleration due to gravity as constant. Okay, and so we can think of this as a function of two inputs, t and Vy, and then the output is just Vy times t, take away g times t squared divided by 2. And so we have this function here, y, which is taking our two inputs, t and Vy, and it's giving us this output that's representing the kind of vertical displacement of our particle, given this time t and this initial upwards velocity vy. And so once again, we can plot this situation using a kind of two-dimensional surface in three-dimensional space. Okay, so we've already seen that there's a surface plot which tells us about the very kind of simple horizontal motion which happens in these kind of systems. Now, the vertical motion is a bit more complex, but we can also picture it using another kind of surface plot. So this time we have these two kind of axes which are giving our sort of inputs, the red one giving time and the green one giving the initial vertical velocity, and then the blue axis here is going to give us the output, which is going to be the height of our projectile at that particular time, given that particular initial velocity. So if we have any sort of point which is on this plane described by the red and green axis, then we can look at the coordinates of that point and use our equation, which we were looking at before, which is that y is equal to vy times t, take away gt squared over 2, and we can plot that as the sort of height of this surface above a particular point. And so essentially then this surface, which is another hyperbolic paraboloid, is so essentially this surface here is describing the kind of vertical motion of our projectile. This is easier to see if we think about what happens when we pick a particular value for our initial vertical velocity vy. So here what I'm doing is I'm selecting a value of vy, and then when I've picked a particular value of vy, let's say 2, that would then be the initial vertical velocity of our particle. And then I'm cutting the surface with a plane of all of the points which have that coordinate vy. And you can see that that's cutting our surface in a parabola. And that makes perfect sense, okay, because what this is basically saying is that at time 0, our particle is going to be at 0, it's going to be at height 0, and then it's as time increases, you can see by moving your finger along the red axis, the time axis, the particle is going to be going up until its kind of initial velocity of 2 kind of gets spent and it starts to fall to the earth, and then the particle is going to continue falling more and more rapidly as it accelerates down to earth. So you can see that that's what happens when our initial sort of vertical velocity is positive, that the thing initially goes up, but eventually the deceleration due to gravity catches up with it. So, okay, now we get to the really interesting bit, the bit where we start to look at this in a more kind of high dimensional way. So let's have a look at our situation. We know that we want to describe the trajectory of our particle, and it has a horizontal and a vertical component. Now, we've successfully done this problem, like on the surface of it, but now we want to really visualize what's going on in a complete kind of way. So firstly, what's going on with this horizontal component? Well, we found this function here. It takes in a time t and an initial velocity vx horizontally, and it gives us the displacement x. And we've also worked out what's going on with the vertical components. We have this function that takes in a time t and a initial vertical component vy, and it gives us the vertical displacement of our particle y at that time. Okay, so we have these two functions. We have them here, look, x of t and y of t. So now what we want to do is to kind of put the system back together, because really the way that we can think of our system is that we pick a time t and a initial horizontal velocity vx and an initial vertical velocity vy, and then given those three pieces of information, given kind of vx and vy, which are like telling us how we're launching this projectile, as well as the time we're interested in, we're going to have a particular horizontal displacement of our particle, which is going to be x, and we're also going to have a certain height of our particle, which is going to be y. Now, the normal way people like to think of this kind of situation is that we specify the initial velocities vx and vy, and then we're going to have a sort of trajectory of our particle where x and y are going to be changing with time. You can think of time as going forwards as my pen's drawing this curve. But you could instead say that we actually choose the vx and the vy and the time, and then we get a particular horizontal and vertical displacement of our particle at that time. And you can see that we can work these two things out together. Okay, so we can say that given these three things, t, vx, and vy, given these three inputs, we get these two outputs. And we even know the equations of these two outputs. X is going to equal t times vx, and y is going to equal t times vy, take away gt squared over 2. So that's fine. But how do we visualize this situation? How do we picture what's going on? And this is where I think things start to get quite interesting. So for a start, we've already seen these kind of situations where we have two variables and we want to plot a function of those two variables. And we see that we can plot that kind of situation as a surface. And so think about a literal surface, like say a desk or something. And so it has an x and a y coordinate. And then we're going to plot the temperature of that surface at different points. We can do that, and we can do that with a 3D plot. Now think about a situation where we have a three-dimensional room and we're interested in picturing the temperature. Okay, so we have these three different directions we can go, x, y, and z, and at each of those points x, y, z, we have a particular temperature. So we'd like to picture that as a four-dimensional kind of plot if we could, right? So we'd like to sort of show that there's a number or a height, which represents the temperature, at every point in three-dimensional space. And so it's kind of funny to think that the temperature distribution in a room is, in a sense, a kind of thing that you should visualize in 4D. But now suppose in our room we have two numbers which we're interested in visualizing. Let's say the temperature and the amount of radiation or something. So then we have a situation where at each point in 3D space we have these two different numbers that we want to picture. And we'd actually need 5 dimensions to visualize that. And that's just the same. And that's just the same as this kind of situation we have here. Okay, we have these three different numbers which are like the heights, width, and depth in our room, for example, although we're calling them t, vx, and vy, and we're thinking of them as having different physical interpretations. But we have these three different numbers that we can vary, and for any sort of triple of those numbers, we have these two different outputs that we want to visualize. Okay, so we really want to be picturing this kind of situation as something that's happening in 5-dimensional space. And in fact, we can think about this a lot more clearly. Okay, so really what we want to be visualizing, and I'll just sort of write it out, we want to be thinking about the set, so this means the set of, and we want the set of times t and horizontal velocities vx and vertical initial velocity vy and displacement x and displacement y, which are going to be such that we have two conditions holding. We have that x is equal to t times vx and y is equal to t times vy, take away gt squared over 2. And what this set is this is a subset of 5-dimensional space. Now let me explain. What I'm saying here is that we're interested in all of the kind of quintuples or 5 tuples of numbers, the first number called t, the second number called vx, the third number called vy, and so on, but these are just names. So we're interested in the collection of all of these 5 tuples of numbers, or if you like, points in 5-dimensional space, which have these two properties. They have the property that this equation holds, so in other words, that this number is equal to this number times this number, and also that this equation holds, in the sense that this number, and this number are related according to this equation. So that's it. We're just interested in like all of these 5 tuples that have this property. And this, remarkably, this is actually going to be a sort of 3-dimensional hypersurface in 5-dimensional space. Like, how cool is that? And we can even understand really what this thing looks like in some sense. So why do I say it's going to be in 5-dimensional space? Well, because it's basically a load of 5 tuples of numbers. A 5 tuple of numbers is a point in 5-dimensional space. Why do I say it's going to look like a 3-dimensional hypersurface? Well, because we can move around this space just by varying these 3 numbers, t, vx, and vy. And as we do that, these x and y are going to get fixed because we know that these equations have to be obeyed. But okay, I mean, isn't this like simple mathematics made difficult? Haven't we taken a situation where we can visualize it easily and then said, okay, well, let's look at it in 5-dimensional space. Maybe that's not such a great thing to do. Well, maybe, but the thing is that we can actually get some intuition about what this kind of hypersurface looks like, really using the kind of situation that we've already explored. Okay, so in particular, let's have a look at what we've already pictured, these 2 surfaces. So let's start with this surface that we've already pictured, showing what's going on with the vertical movement. So when you think of that as something in 3D space, and it consists of the time and the Vx and the x, which has the property that x is equal to t times Vx, okay? This is that first surface which we pictured, and we saw that we could picture it as a subset of 3D space. In other words, it's a surface in 3D space. And so let's call that surface Sx. And so now what I'm going to do is something a bit funny. I'm going to take this surface Sx and I'm going to add some extra sort of variables into it. I'm going to add some extra sort of information, and it's going to make it quite different geometrically. It's going to make it higher dimensional, but in a way that's very simple, and I think you'll be able to understand. So we'll take this situation and we're just going to add in a couple of extra numbers, Vy and also y. So now we're interested in all of these 5 tuples, and we'll call and we're interested in these such that the same equation holds. So x is equal to t times vx. So let's call that that set, we'll call it Sx bar. Now, how do we think of this? Well, firstly, it's going to be a subset of 5-dimensional space, if we're really being literal about things. But it's actually a lot easier to think about this Sx bar, because really what we can think about is we can say that Sx bar is really going to look like what we get if we take Sx and then we multiply it by r squared. Now, what do I mean by that? Well, what I mean is that this thing here is just a 2D surface in 3D space, and it just consists of a load of triples of numbers which satisfy a certain property. And now we've taken all of those triples and we've added in a couple of extra numbers, which are Vy and y, but we haven't got any constraints on what Vy and y are supposed to do. They could be anything. So basically we've got all of these points of Sx plus an extra sort of plane of initial, plus an extra sort of plane of extra numbers. We can take any of these triples, and we can also, to those triples, we could add any value Vy and any value y. And so those give us a load of 5 tuples of numbers, but we can get all of those 5 tuples just by getting this kind of collection of triples and then adding to each of, so if we take a triple in here, we can then add to it any value of Vy and any value of y. And so we get a sort of plane for every triple in here. So we've essentially sort of multiplied this set by a plane, if we like. And that's how we've got this kind of surface in 5-dimensional space. Hypersurface. Okay, so let's carry on. Now let's think about the horizontal component of what's going on in this situation. So we'll think about that surface that we pictured before, Sy. So this is just going to be a simple kind of surface in 3D space, and it consists of the t and the Vy and the y, which have the property that y is equal to t times Vy take away gt squared over 2. And again, that's just going to be a subset of 3D space. So this is just the surface that we've already pictured. Okay, there's nothing fancy about this. It's just a load of triples of numbers which satisfy this kind of property, and therefore are basically telling us about how our particle is falling. But what we're then going to do is basically the same kind of trick that we did before. We're just going to sort of puff out this set so we can think about it as something in 5-dimensional space. So we're going to form a new set that we're going to call Sy bar. And so now we want all of the 5 tuples of t, vx, vy, x, and y, which are just such that this equation we've just wrote holds. So t times Vy take away g t squared over 2 equals y. And now this is a subset of 5-dimensional space. And really we've just got this new set, Sy bar. We've really just got it by taking our old set, Sy, and just again kind of multiplying it by a plane. Okay, So this is really what this SY bar looks like. Because how did we get SY bar? Well, we really just sort of took this kind of surface, SY, which naturally represents our vertical movement as a plane as a surface in three-dimensional space, so as a load of triples. And we just took this collection of triples, and then for every one of these kind of triples, we then added these extra kind of numbers, Vx and x, and they were allowed to be anything, because the only equation that we're having in this set SY bar is just this one here about vertical motion. And so really the way that we got this SY bar is just by taking this SY and in a sense doing a sort of product of it with a plane. And now once again we have this subset of five-dimensional space. And so now we finally reached the punchline, because what is this kind of five-dimensional hypersurface that we're interested in that's telling us everything about our projectile movement? Well, it's the collection of five tuples, so t, vx, vy, x and y, such that these two equations hold. In other words, such that the horizontal and the vertical motion of our projectile are described properly. But then how can we get this? Well, we can just take this SX bar collection, which is telling us about our horizontal motion, and we can just do the intersection of this SX bar hypersurface with this SY bar hypersurface. Why? Well, because these are the five tuples which are satisfying our first equation, and these SY bar, these are our five tuples which are satisfying our second equation. So these are the five tuples where our idea of horizontal motion makes sense, and these are the five tuples where our idea of vertical motion makes sense. And so if we take the intersection of these two sets, as in if we take the set of five tuples such that they're in this set and in this set, the places where these two hypersurfaces cross, then we get this hypersurface here, the collection of t, vx and vy and x and y, such that x is equal to t times vx and y is equal to t times vy, take away gt squared over 2. And this is a three-dimensional hypersurface in five-dimensional space, which represents all the ways that our projectile can move over, in horizontally and vertically, depending on the time and the initial horizontal and vertical velocities. And what we've seen is that just like we can basically solve this problem by decomposing it into a horizontal and a vertical component, so we can represent this kind of hypersurface by thinking about two sort of surfaces, two-dimensional surfaces in three-dimensional space, and puffing them out into 5 dimensions by multiplying them by planes and then intersecting them together. And that gives us this hypersurface in 5-dimensional space. And I find it so remarkable that there's such lovely high-dimensional geometry behind something so simple as throwing a ball. So if you think about more complex situations in reality, like say a double pendulum or a three-body problem, or what's happening in a city with millions of people and all these particles and all the rest of it, it really gives a kind of impression of the kind of amazing high-dimensional geometry that could be thought of as being at play behind reality.